Okay, this is 1620 Cup 2, and we want to investigate slip fields and Euler's methods. And what we're talking about is an introduction to differential equations. So again, with a definition of differential equations. So what are they? It's pretty simple. It's just an equation that has a function and some of its derivatives floating about, and that's about it. And you've got to solve for the particular function that fulfills the equation. Right? So it's an equation in terms of x, y, and derivatives of y. You've done differential equations already. You probably were not, maybe didn't explicitly say you were doing a differential equation, but anytime you do an antiderivative, you're doing a differential equation. So for example, if you were given f prime of x equals 3, which you could also write as dy all over dx equals 3, or if you'd rather y prime equals 3, this thing is a differential equation. We can include x in there if you want. Okay, so this guy has a derivative of y. It doesn't have y explicitly, but it does have a derivative of y, and then it has x floating about. And we learned how to solve these things, right? So you just find the antiderivative. So I want to solve this thing for y. Okay, so an antiderivative would be y equals 3x squared over 2. And this would be called a particular solution to the differential equation. But we know there's this issue, your teacher probably took off points. You always have to put in plus c, right? So that would be the general solution to the differential equation. Okay. Okay, so right, you've done these already. It's no big deal. So some other maybe definitions. The order of the differential equation is just the highest derivative that you see exhibited. So the order of your differential equation, which I'll just write diff eq, is determined by the highest derivative. Okay, so for example, y double prime plus y prime plus y equals 0 is order 2. And you see there's kind of looks like a polynomial or something like that. And there's connections to that you'll explore once you get to differential equations later on, a real class in differential equations. Okay. Right, so in the beginning of the book, they're going to have you basically work with checking to see whether or not something's a solution to a differential equation. This goes along the same lines as when you started out in algebra and you were given something like 3x plus 2 equals 5. Check to see if x equals 1 is a solution. Right? It's that idea. And how do we do that? Well, we put 1 into 3x plus 2. And sure enough, that equals 5. So it is a solution. Okay, so we're going to follow that same kind of program here. where they give you the solution, you check to see if it works, and then we'll start giving you ways of finding those solutions. Okay? And then you'll just work with more and more complicated types of differential equations and learn all kinds of ways to deal with them and all kinds of cool stuff. Okay? Okay. So let's look at number 1. We want to verify whether or not this thing is a solution to the differential equation. They give us the differential equation as y prime equals 4y, and then y equals c e to the 4x is our potential solution. So the way you want to do it, and the way at least they'll teach you in some differential equations classes, start on one side of the differential and move to the other. And this is your given information. And you could expand this information to include derivatives. Okay? Taking a derivative of this thing is legal, so to speak. So we'll take its derivative because we need the derivative for this equation. So y prime is c e to the 4x, and then the chain rule multiplied by 4. So we'll have a 4 sitting there. Okay, so we use all this information to go from one side to the other side of the equation. You could start on the left, start on the right, it doesn't matter. You can also start separately and then show that they get together in the middle. But ultimately you want to write in a way that people can read it. So here we go. You may have to do a little work first, right? A little scratch work and then put it all together, but this is what it should look like in the end. So starting on the, and let's start on the, let's see how I did it in my notes, the right-hand side. Okay, starting on the right-hand side, we note 4 times y equals, and then we use the given information, so it would be 4 times c e to the 4x. And then we note that, well, 4 c e to the 4x equals y prime, so we have equals y prime. And then that's the other side of the equation, so we're done. Okay. Let's carry on, maybe look at another here. This one is a bit more complicated, but they usually throw it in your lap. Anyways, so this time the differential equation y prime is 2xy all over x squared minus y squared. And then the solution x squared plus y squared equals c times y. Okay. So again, fair game. You can basically take derivatives of this thing, but you can also manipulate it algebraically if you need to. And we will need to in order to bridge the gap between these two expressions. So first I'm going to take the derivative implicitly. I get 2x plus 2y y prime equals c times y prime. Right? And then I could solve for my y prime. So 2x equals cy prime minus 2y y prime. And then I'm going to factor out the y prime and divide. You'll end up with y prime equals 2x all over c minus 2y. Okay. So you can start trying to make these two sides equivalent. I'll start on the right-hand side this time. So starting on the right-hand side, I note, all right, so then we have, well, crud, I should have started on the left, I mean the left-hand side, not the right-hand side. There's a mistake in my notes. I'll fix that later. Starting on the left-hand side, I note y prime is equal to 2x all over c minus 2y. Okay, this is kind of an issue because I don't know what the heck c is, and this formula here didn't have any c's in it. So another thing I could do is, like I said, algebraically, you can solve these things for other variables. So in particular C, if I were to solve that guy for C, I'd have C equals x squared plus y squared all over y. Okay. So I'll just take that expression and plop it into here. So this will equal 2x all over x squared plus y squared over y minus 2y. You know, multiply both top and bottom by y. You end up with 2xy all over x squared plus y squared minus 2y squared after I distribute this y. And you could simplify this and you get 2xy all over x squared minus y squared, which is the right-hand side, which is what I wanted to show. Right? Okay, so that's probably as hard as it'll get. Let's maybe take a look at another one, 35. This time we want to verify the solution and find a particular solution. So they give us y prime plus 2y equals 0, and want to verify y equals c e to the negative 2x as a solution. Then we also want to find the particular solution associated with 0, 3. Okay, so first I'll verify, find its derivative. Y prime is negative 2ce to the negative 2x. I'll start on the left-hand side. Starting on the left-hand side, I note y prime plus 2y equals, and then I use my given information, that equals negative 2ce to the negative 2x plus 2 times y is ce to the negative 2x. And then, of course, that equals 0, which is the right-hand side, which is what I wanted to show. Okay. Okay, now the particular solution part, what you need is this ordered pair. So what this represents is a bunch of curves in the plane, and you need to figure out which one of them is the particular one that goes through this point 0, 3. Okay, so all you have to do there is plug this into this formula and solve for c. All right, so let's try that. Y is 3. X is 0, so ce to the negative 2 times 0 is ce to the 0. So 3 equals c. And then our particular solution, y equals 3e to the negative 2x. Okay. For a lot of these differential equations, you're not going to be able to easily find that solution that was given to us on our plate. So they developed a lot of kind of graphical methods for analyzing these things, like phase portraits you'll see later on, and stuff like that. And these aren't as, you know, they won't put any mathematical hair on your chest, so to speak, but they are legitimate and they work. And oftentimes it's better than the old-fashioned way of going out into the woods and chopping down trees and building a fire and boiling water and then making your dinner. You know, just use the microwave. Okay, is what we're talking about. So, anyways, slope fields is a great way to get an idea of the solution to the differential equation. Slope fields. And basically, it's just a bunch of little tick marks based off of the differential equation. It's a graph of the slopes of the solution curves. So, for instance, we can make one up. For example, one that we know the solution to, right? So, our differential equation will say y prime equals 2x, right? So this is unusual because it's unusual because we know the solution. I mean, typically you're not. We know the solution by taking its antiderivative will be y equals 2x squared over 2. In other words, x squared, and then, of course, an integration constant. Okay, but the idea is you don't know, right? You don't really know in truth what the thing will look like. We pretend. We know this, but let's just pretend. Okay, so I want a slope field for this guy, and hopefully from there we'll see these guys pop out. So to get the slope field, you just do a chart. You have x, and usually you'll have y. In this case, we don't have a corresponding y, so it is kind of a silly version of a differential equation, but that's okay. It's just, it'll be easy. I'm going to do an xy plane, and you just pick random points in the plane that you're interested in. Okay. We'll just pick 9 points. So here, 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 here. Okay. And we want to find the slope of the solution at all those points. And this gives you the slope of the solution at those points. So let's try to figure that out. So for these 3 points, the coordinates are -1, 1, -1, 0, -1, 1. And then for the next 3 points, 0, that should be -1, I guess. 0, -1, 0, 0, 0, 1. And then the next 3 points, 1, -1, 1, 0, 1, 1. It's very time consuming. You guys don't understand the pain because back in my day, you had to do this all by hand. I mean, literally, it was a mind-numbing experience, which did not make you any smarter in the long run. But I did it. You can too. This is an easy example. It's just one. So I'm plugging these xy's into this formula here, okay, the differential equation. There is no y, so you don't put anything in, but you put it in for x. So -2 is the slope of the solution curve there, and then so on. Here it's 0. When you plug 0 in for x, you get 2 times 0 is 0. When you plug 1 in for x, you get 2 times 1 is 2. Okay, so what we're going to do is put a bunch of little tick marks representing the slope of a little tangent line at all these 9 points. So -1, -1 down here, we said the slope is -2. So down 1, 2 over 1, excuse me. The slope will look like this. And then also the slope will be the same for those other guys. Maybe we should put that in a different color. Okay. And then for here, the slopes were all 0. So you get like a horizontal line. And then here, here, and here, the slopes were all 2. Okay. So the tick marks kind of serve as a maze, so to speak, where if you draw through it, you can get a picture of your solution for a particular point. So if you wanted the particular solution that went through 0, 0, you might get something that looks like this. If you want the particular solution that goes through -1, -1, like over here, you'd probably get something that looks like this, and so on, right? So even if I didn't know the actual solution, which was a bunch of parabolas, which is kind of what we're getting here, if I didn't know that, I could draw this thing and then just kind of fill in the solution curves. And it works, okay? You don't have to do any algebra for that, which is nice, especially if this doesn't have a way of being solved, which happens a lot, right? Okay, so slope fields are a very powerful method. And don't underestimate it. Just because it's not going to make you look cool in front of your friends, it doesn't mean that it's not worthwhile. Okay? All right. The next method is also another method for when your sort of algebraic tools fail you. And it's called Euler's method, and it's an approximation method. Okay, so let's take a look at that guy. In the real world, they have more complicated methods for doing these approximations, but they're all sort of, in a weird way, based off of this Euler's method. So it's a good introduction to the later numerical methods for solutions. So y sub n is equal to y sub n minus 1 plus some, and actually it's used in machine learning, isn't it? This would be like a learning constant or something like that. And then times f of x sub n minus 1 comma y sub n minus 1. Okay. So this tells you where the next y value is based on a previous x value. And you'll be moving through a plane in some sort of way. So the way it'll work is you have a differential equation, dy over dx, which kind of describes the slope at any given point on your curve. So it'll be in terms of x's and y's, your differential equation. So you'll start here, maybe, if you want to know something about this region, and you'll use this differential equation to find the slope at that point. So you would do kind of like a slope field, you get a tick mark at that point, and then you would use that as an approximation, a linear approximation in this region to the actual curve, okay? And then you would move some h value to your next point. Okay, so you would move like up to here, and again, you would take this point, plug it into your differential equation, and maybe get a different slope. Okay, so maybe the slope is like this here, and then you would move over by another h value, and use the slope from there to get to the next point. And then you would figure out the sort of slope, the tick mark there, maybe it's going down all of a sudden, and then use that to get to your next point. And you end up with this kind of polygonal approximation to the solution curve, whatever the solution curve may really be. Maybe the solution curve looks like maybe something like this. So one takeaway from this little picture is the farther away you get from your initial value, the worse your approximation will probably be. And on top of that, if you use smaller increments, the better this approximation will be as well. Okay? So that's Euler's method in a nutshell. Let's take a look at 73 and see if we can actually compute one of these thingamajigs. Okay, so 73, we given our differential equation y prime is x plus y. Y of 0 is 2. N is 10. That's the number of little line segments I want. And then h, the distance between the consecutive x values, will be 0.1. This thing here, this y prime, that's your f of x comma y. Okay, the book will probably do kind of a chart thingamajig. So you'll have an n value, and then your x sub n, and then your y sub n. Okay. You want to start at your initial value. So n equals, when n is 0, I'll have this point 0 comma 2. Okay. And then you use the h value to get to your next x value, and you want to do this 10 times. Okay. So 1, 3, 4, 5, 6, 7, 8, 9, 10. And usually, you're going to do it with a computer later, but you want to do it by hand just to see how it works and see what you're dealing with. Okay. So this will be 0.1. That's the h value. That's how far we're moving to our next point. And then 0.2, 0.3, 0.4, 0.5, 0.6, 8, 0.9, and then 1. Right? Okay, I'm going to have to do a little work to find these y values, and you use this formula to do it, the Euler formula. So let's go ahead and take a look at that. So again, x sub 0 was 0. Y sub 0 starts at 2. Okay. And then x sub 1 is 0.1. And then y sub 1, I have to use the Euler method formula. So you use the previous value, 2, plus h, which is 0.1, times f of 0, 2. Okay. So 2 plus 0.1, 0, f of 0, 2. So I'm plugging 0 and 2 into my formula. So it would be 0 plus 2 is 2. And then 2 plus 0.2 is 2.2, and that'll be my first value. So it's it can be a little slow going, especially if you have to do a huge one. And if you make a little mistake in the beginning, it's, oh my gosh, it's really annoying. And so again, y2, I use the previous 2 points. So I'll go 0, the y sub 1 is 2.2 plus 0.1 times f of 0.1 comma 2.2. So that'll be 2.2 plus 0.1 times f of that. So 0.1 plus 2.2. And then when all is said and done, that will be, so 2.2 plus 0.1 times 2.3. So that'll be 2.2 plus 0.23, and that'll be 2.43. Okay, and then you just keep on repeating that process, and at the end you'll have 5.78, which becomes an approximation for what exactly this mystery function would evaluate to at 1. So I don't know what y is. I have not solved this thing for y. All I know is this differential equation. But now you could say, if somebody asked you, y of 1 is equal to 5.78, I think, right? Okay, so that's the idea of Euler's method.